Hi.
Hey.
Hey.
Point the light, it'll really confuse.
We'll find out. This is one of these new cameras. That's right. Why are y'all lurking back there?
So then somebody has to come sit in, they don't have to walk past everybody.
Yeah, that's the
Yeah,
way
that
it
makes
works.
sense. Yeah.
That was well
It's
done.
very convenient
Oh, I know.
and polite to everyone.
We're special that way.
So some of that's what plans
Yeah, that's what we do. Except for Dr. Summers, he always sits there, you know? He's always in the way.
Stand where you're going to be so we can kind of calibrate this thing.
I like
This
your
is not
tripod.
blocking anybody?
Oh, really?
Do what?
I like your tripod.
Yeah.
It's actually a monopod.
A monopod, yes. That's what it is. I guess you can't have everything.
It's actually a based on computer science.
Yes.
Thesis defense for my work of using unrestricted mobile sensors to infer tapped and traced user data. And first I want to thank my thesis advisor, Dr. Touchain, for all his help that he's given me, both with this work and my entire time here at CSU. I also want to thank Dr. Bakir for agreeing to be on my committee and all of you for coming to support me and watch my thesis. So for this work, we really had one main question, and that was, is it possible to use gyroscope? Oops. Yeah, sorry.
You got your snacks and stuff in here. I'll tell them to get it. Okay.
You're in the video. Hi. That's great. We had a record.
Sorry.
Yes.
The main question is, can you use gyroscope and accelerometer data to infer user traced inputs? And then we had a sub-question that was dependent on that main question, which was, if you can infer these traced inputs, how do different classification algorithms affect that inference in terms of speed and accuracy? So before I go into our work, I wanted to first define some of the terms that we use throughout the thesis work. So first off, a tap is an input where you enter one letter. On the other hand, a trace is an input where you enter a whole word. And you do this by starting at the first letter and moving through the letters of the word until the last letter and then raising your finger. This style of input was made popular by the swipe keyboard, and it's available in a lot of the third-party keyboards as well as the Samsung default keyboard. The other word I want to define is unrestricted. So in the Android environment, applications are run in application sandbox, and they're run separately with separate IDs, separate processes, and they have separate restricted access to limited resources. If a particular app wants to gain access to more resources or to protected APIs, it has to explicitly request this permission, and has to do this in its manifest. And when it requests this permission, when the app is installed, a user has to agree to these permissions before the app can actually be installed and run. So for example, if an app wants to use the camera, it has to request this permission. If an app wants to use the microphone, it has to request this permission. So as you can see from this, these are two examples of restricted resources on the Android environment. So Android actually supports many different types of sensors. You see there's motion sensors such as the accelerometer and the gyroscope, as well as other more interesting sensors slightly, like the humidity and temperature sensors. The actual sensors that you're working with, however, depend on the device you're working with. So for example, with the Galaxy Tab Pro, you only have the accelerometer and the gyroscope. With the Nexus 5, you have those in addition to the pressure and proximity sensors. What all of these sensors have in common is that they are unrestricted. They don't require any permission. And this means that any application at any time can use this information, the data drawn from these sensors, without the user knowing about it. So previous work has already demonstrated that this freely available sensor data is sufficient to infer user taps on mobile systems. And they've done this both on the iOS system and the Android system. All of these work have kind of an overarching methodology of using sensors to collect raw data, and then from that raw data, extracting features that represent those taps. They then use those features and a classification algorithm to test and train a classifier to be able to infer unknown user taps. So even though they have this overarching methodology that they share, there's still a lot of differences between these works. So starting off with the sensors that they use to actually collect the raw data, you see that they all used motion sensors. The most common motion sensor they used was the accelerometer. The second most common was the gyroscope. In works that use both of these together, the authors noted that the gyroscope really provides much more for the inference accuracy. It contributes more to the inference accuracy than the accelerometer. However, you can see that some works use just the accelerometer separately, and they were still able to infer taps. The feature set's another place where you see huge variety. The size varied from 7 to over 270 features. However, in one of the more recent works, the author noted that none of these works appear to be obviously significantly better than the other feature sets. Another area of variation was the classification algorithms used. As you see, there's really not a lot of overlap. This one, in this work, Tap Prints, they actually used an ensemble of ensembles method, where they used many different classification algorithms and a voting system to be able to get their predictions. And of these, only one work, Kai and Chen's, actually compared two classification algorithms and their performance. And they compared dynamic time warping and support vector machines. And these authors concluded that there really was not a big difference between their performance. So you see there is variation between their methodologies, but they're all able to infer taps. What we wanted to do was to extend their work to infer traces. And the reason we thought to do this is because traces are available in modern Android systems. And it's very realistic to assume that some people will prefer to use traces over taps, or use a mixture of taps and traces. So moving into our work, we decided to split our work into two phases. The first phase, we wanted to look only at taps, and that was so that we could verify that our approach still was able to do what previous work could do. And then in our second phase, once we verified that our approach was working, we started to introduce traces. Of course, before we could really do our experiments, we had to make our own decisions about the sensors we were going to use, the feature sets we were going to use, and the classification algorithms we were going to use. So for the sensors, we decided to use the gyroscope and the accelerometer. We had two reasons for this. The first is that they're very common. So if you can see from this breakdown from 2014, 94% of the surveyed devices included an accelerometer, and then 71% included a gyroscope. And you can actually see this is part of a motherboard from the Samsung Galaxy S5. Right down here is the gyroscope and accelerometer. Our second reason that we use these sensors is that previous work has already shown that they both contribute to inference accuracy. For our feature set, because there was such a huge range in the number of features used before, we tried to go sort of middle of the road, so we ended up with a total of 36 total features, including the min, max, median, skewness, and kurtosis. As you can see, compared to previous work, we tried to include at least one feature from every work that we reviewed, except we did not have one in common with Kai and Chen. One of the major benefits of the feature set that we chose was that it was computationally efficient. And this is very important when you're working with large data sets, because this helps reduce the amount of time that it takes to actually extract these features from the raw data. And this is very important to help prevent time from being a limiting factor, because it couldn't be very expensive if it takes a long time to extract these features from raw data. Because we wanted to compare the effect of classification algorithms, we chose to use classification algorithms that really ranged in relative complexity. So our simplest that we used was k nearest neighbor, where k is equal to 1. We also used random forest, and then our most complex was support vector machine. And again, you can see compared to previous work, we tried to have some overlap, although there is one work where we had no overlap. For these algorithms, we decided to use the default algorithms that are available in Weka, which is a machine learning application that is freely available. We also decided to use the default parameters, and we had two reasons for this. The first was repeatability, so that if somebody wanted to continue our work or repeat our work, it would be easier for them. And the second was because since we only used one user's data, optimization likely isn't generalizable, so it's probably not valuable. So we decided to go default parameters and see how well they worked, even with just that. So after we chose these, we were able to actually form our approach. And in our overall approach, we assume that a user is typing on a device that's infected or has installed an application that records the motion data while they're typing. So this is actually what that data looks like when somebody is tapping. So you see up here you have the X, Y, and Z axis of the accelerometer, and here is the X, Y, and Z axis of the gyroscope. You can see with these yellow lines, I'm not sure if you can see them in the back, these are the end times of each tap. So you can see each tap on a device is very distinctive motion. So this raw data is actually stored as a CSV file, and it is transferred from the user's device to a PC, not the user's PC. And this PC is where we do all the processing, the feature extraction, and the classification. And the reason we do that is because if we were to do these activities on a user's device, it would take up their CPU, it would drain battery, and it would take up space. And these are all factors that could lead a user to noticing that something's happening on their phone that they don't want to happen. So once the raw data gets to the PC, that's where feature extraction occurs. And when we get the features, we feed them to a classification algorithm. This classification algorithm is trained on labeled data. These are features that we know represent a certain word or letter. And then that classifier takes a prediction of what the letter or word the user types is. So to really be able to do this approach, we had to use 3 different applications. So the first of these applications was an Android app that collected motion sensor data. So this app was a little more than 200 lines of code, and it creates 3 CSV files. One for the gyroscope data, one for the accelerometer data, and one for the end times of taps and traces. The second application we made was a Java application for feature extraction. So this was a little over 360 lines of code, and it took those CSV files from the Android app and created one CSV file that contained all of the features for all of the taps and traces that were in that raw data. And this feature extraction program, it identifies taps and traces based on that end time and an assumed length. So, and of course the third application we had to use was Weka, and it uses an ARFF file as its input. So before the CSV file finishes from here, we have to convert it so it can be used. And then that's where all of our classification and prediction occurs. So in our phase 1 experiments, we used a Galaxy Tab Pro 8.4 in portrait orientation. We assumed a tap length of 200 milliseconds based on previous work, and you can see here on the right, these are the X and Y axis of the gyroscope for the letter H, assuming 200 milliseconds. So this is actually what the feature extraction program uses to get those min, max, mean, median skewness kurtosis. So we collected 50 taps per letter for a total of 1,300 taps, and we did 2 different tests, a 10-fold cross-validation and a split test set training set. And then here are our results. This is for the 10-fold cross-validation. You can see that KNN took the least amount of time to build, which is kind of what we assumed because it is the simplest relatively. And then support vector machine took the most amount of time to build, which again we would assume considering its complexity. In terms of accuracy, you see that both random forest and support vector machine performed better than KNN, where k is equal to 1. However, they don't perform significantly better than each other. They both perform pretty well in this case, over 80%. Of course, with taps, even if your inference is incorrect, you're still able to get some extra information. And this is because of the confusion matrix. And if you look over here on the side, this diagonal are all the letters that are predicted correctly. And then above and below it are the most commonly predicted incorrect letters. So as you can see, the most commonly confused letter with F is G. And this makes sense because if you look on a keyboard, F and G are very close to each other. So even if your interpretation is incorrect, you might still be able to get a second guess that is correct. So it's a little bit of extra information. So in the 20%, 80% split test set training set that we did, we get similar results. K&N, least amount of time to build. Support vector machine, most amount of time to build. And again, random forest and support vector machine are much better than K&N, but very similar to each other. And you actually see that the numerical highest switches. So it's pretty obvious they aren't that different from each other in accuracy. So how well is this really letting us guess the user's letters that they're typing? So compared to random guessing, which is less than 4%, using the gyroscope and accelerometer lets you predict what a user is typing or infer what a user is typing 18 to 20 times better than random guessing. So this is fairly good. And actually, I should point out that our accuracy is higher than previous work, but that's kind of what we expect because we are only using one user's data. As you add users, you add variation. Variation in how a user holds the device, variation in how a user types. So you would expect, as you add more users' data to this, that the accuracy would fall some. So at this point, we said, yes, okay, our approach will work for taps. So let's extend it to traces, or attempt to. So over here you can see the X and Y axis of the gyroscope for the trace of hello and the trace of catch. You can see they're much more complex than a simple tap. So when you go and look at trace inputs, we decided there were two main considerations for us. The first was word choice, and the second was timing. In terms of word choice, we actually decided to split this phase into two separate experiments. The first was a pangram experiment, where we use a pangram as input, and the second was a common word experiment, where we use 110 common words as input. The reason we chose to do this is because we wanted to still be able to cover the entire keyboard and include all of the letters, but we also wanted to use words that were relevant and likely to appear in conversations. So the second concern was timing. This is a big concern because we're assuming a length. So we chose to assume a length of 1 second per trace. And this was based on Swipe's claim that somebody could trace 55 words a minute. However, this is obviously a very big assumption because words are very different. They're different in length, and the letters are different distances apart on a keyboard. So the trace for two words of the same length could be very different. And actually, we had to use a second assumption, 0.5 seconds for short words, because you can't have just that one assumption. So when there were many short words, we had to use half a second instead. So for our trace experiments, we again used the Galaxy Tab Pro 8.4 in portrait orientation. And as I said, we used the assumed length of 1 second for the pangram, where all the words are a bit longer, and half a second for the 110 common words, where there are some shorter words. We again did 50 traces per word, for a total of 40 traces for the pangram, and 5,500 traces for the common word experiments. And we did both the tenfold cross-validation and the split testing set training set. So here with the pangram experiment, the pangram that we used was the quick brown fox jumps over the lazy dog. And you see, again, for both of them, what we saw before, K&N takes the least amount of time to build, support vector machine takes the longest. And again, with accuracy, you see that random forest and support vector machine still aren't really that distinct and significant from each other. They both perform almost the same. A little more than before, but still you can see them switching on both sides. But they both are still better than K&N. And if you look at these results, they look very good. They're both almost 90%. But when you think about it, because there are only 8 different words here, the random guess is also relatively high, so over 12%, which means using gyroscope and accelerometer data only allowed us to infer words 6 to 7 times better than a random guess, which still shows data leakage, but not as much as with a tap. Also different from tap is the confusion matrix. So if you look here, the and jumps were always most commonly confused with each other. But if you look at a keyboard and try to trace out those words, you'll see that it's not very intuitive that their traces would be similar. So it makes it a little more difficult to really try to extract some information from incorrect inferences. To make it more confusing, there's non-reciprocal confusion, I guess is the word to say it. As you see here, brown is always most commonly confused with lazy. But lazy is only most commonly confused with brown if you're using a support vector machine classifier. So this can make it kind of complex when you're trying to get some more information out of incorrect inferences. Moving on to the common word experiment, these are the 110 words that we used. So as you can see, there are quite a few words that are only 2 letters, but they aren't the majority. However, that was enough to impact the accuracy that we had to take down the assumed length, which is unfortunate because for bigger words like because and people, that means you're losing a lot of information because you're not getting the entire word. So the features aren't as representative of that word. So that was definitely a drawback. You can see in its results, again, k-nearest neighbor is the fastest to build, support vector machine takes the longest. In this case, over 13 seconds for both of them, both tests. And this is with 5,500 traces. So you see, the time required goes up quite a bit. This time for accuracy is the first time that support vector machine is significantly better than both of the other classifiers. And in this case, it was over 40% in both tests, which may not seem that great compared to what we've seen before, but if you compare it to a random guess, which is less than 1%, using the gyroscope and accelerometer data allowed us to infer traces 27 to 47 times better than a random guess. And this 27 times better is if you're using KNN, which you don't have to use. So from this we concluded that yes, to some extent, you can use accelerometer and gyroscope data to infer traces. Up to a little more than 40% for 110 words and 90% for pangram, which is 8 words. Ours was 8 words. Of course, the true extent and significance of this data leakage due to the gyroscope and accelerometer data, it's harder for us to quantify because our work only used one user's data, it only used one device, and it only used one orientation. And all of these things affect inference accuracy. So obviously, as I said before, if you add more people, you add more variation, the inference accuracy goes down. With the device, actually the bigger the device, the better the inference accuracy. And for all of our work, we use the Galaxy Tab Pro 8.4, which is actually the smallest of the 3 Galaxy Tab Pros. In terms of orientation, we use portrait orientation, and actually, from previous work, this has been shown to be less accurate than if you had the phone or the tablet in landscape orientation. So as I said, all these things really affect inference accuracy. So it is a bit hard to make generalizable conclusions from this. Our sub-questions conclusion was that both random forest and support vector machine do perform better in terms of inference accuracy than KNN, where k is equal to 1. And when there are larger numbers of words, a larger number of labeled classes, support vector machine is significantly better than random forest. Of course, it is a bit of a trade-off because support vector machine always takes the most time to build. So to extend this work and really go forward with it, these are some of my recommendations. So the first and really the most important would be to repeat experiments with a larger number of users. This would really help make the conclusions more generalizable and make it easier for somebody to confidently make or draw a conclusion. It would also make it possible for this second point, which would be to try to make a pre-made learning or training set that could be used to infer somebody's traces or taps who hasn't contributed to that training set. This, of course, would be very important if you're considering this for a type of spyware or malware, because often you wouldn't have access to that person's training data. Another experiment that could be done is to see how larger sets of words, a larger number of labeled classes, really affects the inference accuracy. So we saw going from 8 words to 110 words, we went from 90% to a little more than 40%. What's really the relation there? Another important point that I think should be done or could be done is to modify the feature extraction program so that it puts boundaries on the assumed length. So in that way, you could still extract fully the short words without hindering as much the long words. So you could cut them off and still be able to get more of the long words. And that would be actually necessary for this next point, which would be to infer mixed tap and traces, which this is the most realistic case, because a user could enter their passwords through taps and then their confidential emails through traces. So this really would be an interesting experiment, but this is a prerequisite for it. So, thank you, and do you guys have any questions? Yes?
Nice presentation, thank you.
Thank you.
I just wonder about the feature extractions.
Yes, ma'am.
I wonder how do you decide on the features you're going to use? Have you used like an algorithm or something, or you chose certain features based on certain lessons?
We chose the features for, one was simplicity in computation, one was for overlap with previous work, and the other was how easy would it be for us to actually be able to write something that could get them. For example, one work used a fast Fourier transformation. That would be more difficult for us to actually write and get done than doing this QNIS or kurtosis, which you can use available APIs for. So that was a lot of our reasoning behind that.
Assuming they know how to type, they know the keyboard, because
Yes.
if you try it on me, I would really mess things up.
As long as you're consistent, I think it would still work, actually. But yes, it is kind of assuming that you usually use these keyboards.
With 2 thumbs?
With one. Yeah, because you have to hold the device still. Yeah. Yes.
Yes, coming back to the feature,
Yeah.
all the features that you use, those look like statistical features.
Yes, they are.
So, well, in collecting your work, have you seen people using structural features?
Yes. Yes, there were. And actually the skewness and kurtosis are structural features of the curves. So, but yes, some were very, I think I actually even have a slide for that. Some were very, very structural. I think Kai and Chen's, you see there was the peak times, the peak interviews, attenuation, the vector angles, I think. Yeah, so it was much more structural.
The other comment is related to your approach of doing the classification. You're going to have more error when you increase the number of classes that you need to predict.
Mm-hmm.
So have you thought about maybe diminishing the number of classes?
Yes, and that would definitely be something for, if you could use a pre-made learning set, probably you would be looking for certain words because you're looking, you're spying on somebody knowing what you're wanting to see. So you would choose specific words that you would then build a training set for. And that's what you would kind of filter people's text for. So yes.
Another question.
Yes.
How hard was it to get like more data, like different users' data?
I did collect some other users' data, but there were a lot of problems. One person I collected was left-handed, so I had to get rid of them. But there was, sorry, but it's extra variation that I didn't want to have to. A lot of them failed to get the consistent number of taps and traces. So a lot of, because they were just students in our lab, it takes a long time to actually get a large number. So for the traces, the 5,500, that took about a week to collect all of them. And I did 25 instances when I was getting the students to volunteer for it, but often they still would mess up the number, mess up the, what was it, something else somebody did?
Orientation.
Yeah. Some people would hit the device accidentally, which shouldn't matter, but I did want to keep it as consistent as possible. So there was a lot of, or they'll rest it on something while they're doing it, which of course then you lose some of that motion because it's getting absorbed a little bit by whatever it's laying on. So,
Dr. Chernitsa.
hello? Oh, hi. I just finished, actually. Thank you.
Put him on speakerphone.
But I had read through your slides. Did you get any questions from the committee asking for images?
We're actually actually I put you on speakerphone. They're asking questions right now.
Okay, very good. I'll put my phone on mute and listen in.
Okay.
Hi Chuck, it's Wayne.
He muted himself.
Okay.
Is there a volume?
I think he muted himself.
Yeah, he muted himself, but that's, I think, the max volume, isn't it? Oh, okay, yes. But I think it is possible to get more users' data. It's just, we do kind of need a more controlled environment and more of an incentive than just, please will you do this for me, take maybe 30 minutes, an hour to do this.
So how many users you used for that result?
For all of these, I just used my own. Their data was...
A single user?
Yeah, this single user. That's why definitely it needs to be repeated with more users. Definitely.
And for the result you have obtained, how many times you repeat the experiments? One time experiment result?
It's one time.
If you can do, I know that if you collect data, there's a very complex time consuming, right? So if you can do more than one time, such as a couple of times, right? You
Yes.
can compare the result from different times to see if the result, accuracy, the time used are consistent.
That makes sense.
Look at that result.
Yeah. Yes.
I have two questions.
Yes.
First, why is it that you don't use fast Fourier transform?
I didn't know how to do that in Java.
Oh, well, we could have done.
Oh.
Anyway,
Yes. I was also a little worried that it would take a little bit too long because when I was doing the Fourier transformations for, what's the giant magnet that we use in biochemistry? But it took a long time for that to process. So I was
It
thinking that
depends
would...
on the amount of data.
Yeah,
Yes.
I was thinking that it would be so time consuming that it might be difficult with the amount of data that I wanted to use at the time. So that was one of the
Okay.
considerations.
The second is, since you're using accelerometers and we have the constant acceleration of gravity,
Mhm.
how did you eliminate that? Because that,
Actually, sorry, Android has, it's called gravityless accelerometer. So
Okay.
it's built in so that it removes it. So there's two different options when
Okay.
you're using the accelerometer. You can use the regular pure accelerometer, and you can use that one that's supposedly removing gravity.
okay, yeah, because I saw raw data, and so
Yeah.
I thought that it was the raw accelerometer.
No, it is actually the accelerometer that removes
So
gravity.
it's already been filtered.
Yes.
Okay. All right.
Yes.
I had a question about the length that you chose.
Yes.
It's 1 second, you
1
said,
second, yes.
for land tracing. I mean, how hard will it be to sort of customize it sort of per word type of thing, looking at the location of the letters, how far they are from each other and all that?
I did actually want to do that, and that's, we had started Nathan on that, but then he never finished it because there were misunderstandings. But to actually be able to get the word length when you trace it, you have to have access to when you actually press your finger down first onto the keyboard, which is not information that you can get on a default keyboard. It's restricted. It doesn't let you know that. So you'd actually have to build a custom keyboard first and then use that to calculate how long it takes. Or, which I told him to do, take a screenshot of your keyboard and use it as a backdrop and then fake the timing and record it from there, which we could have done. So it wouldn't be that hard, but then when you're extracting it, you don't really know when the start time of the word is, so you wouldn't know when to finish extracting. So that it would be an issue for the unknown words.
But I feel that, that would actually improve.
It would
the
definitely
inference
improve the
whenever
inference.
you had something more customized for different lengths, or different, not just lengths, but I think it's also the locations of the letters
Yes.
on the keyboard. They definitely make a big difference.
I think so. And that's why I was really hoping to do the boundaries in the feature extraction program, because then you could put a longer assumed length, and if a word ended before then, if it ran into another word or letter, it would stop. So even if you had a tap that was 200 milliseconds and you're assuming 2 seconds, it would still stop and only do 200 milliseconds. So I was hoping to get that finished, but I didn't quite get that working out yet. Yes.
How many samples are you getting from the accelerometer on that time frame?
Okay, it was, I think 4 per second. I have the exact number in my thesis, but I can't think of it. It is the fastest sampling rate, which depends on the device, but for this one I think it was 40, second, I think. I can look it up, but yes.
No, just a comment. It would be nice if this could be extended to have more users, but then to try two things.
Okay.
One is to do like kind of a classifier for each one of them, and you combine all of them, and then take all versus taking all of the information, build only one classifier,
Oh, yeah.
and see how different they are.
Okay.
That would be something that also could be done later.
Definitely.
So you said that the first time that a user basically touches you can't get those information.
No,
And
not-
whenever it does not, like, it stops,
When you stop, yes, you can
you
get
can
it.
get it.
But on the newer Android keyboard, I think you could get it on the older Android keyboard, but you can't get just when you touch on a new Android keyboard. And you can't take screenshots of a keyboard when it's open. There's a lot of new restrictions on the keyboard in the Android system. But yeah, not the start time.
Not to stop.
Yes.
Why the confusion between the and jumps? The trace is completely different.
Exactly, and that's why I was looking at it, I was like, this makes no sense. I'm assuming somehow maybe the motion is similar, but I was trying to think about it and I really didn't see it. So it does make the confusion matrix a little hard to interpret. So especially as you add new words in there.
You were not doing eye tracking, did you?
No.
I was just thinking that if you're actually doing a 4 hertz, right, the sampling, can only, using that, it can only represent 2 hertz signals.
Let me see. Actually, how much I had in there, because I did download my. Because now I want to go to. But I can. Does someone else have another question while I look that up? Because I know I have it in here.
So left-handers trace in a different direction?
Yes. Well, they're also holding in a different direction, so the motion's going to go in a different direction because you're bouncing on this side instead of on this side. So, because you have a different, I guess, the axis of rotation because your holding is still on one side.
So it really confuses people if I switch hands.
Well, if you train the data based on that, it may not matter because it's built in, but you'd be switching your features around probably. So is what I was worried about. So I had to remove his. And that's why I looked this up.
So, time, or there's no time to ask a question?
Yes.
Actually, okay, so I have 2 questions, and both, I guess, will be based on your opinion, based on the work you've done.
Yes, sir.
I read your thesis, and I read your slides. I apologize for missing the early part of the presentation. Okay, so the first question is this. If you were just basing the identification of the user on the signature of their swiping pattern, okay, with a multiple touch point touchscreen, like in the lab I'm working at now, Georgia Tech, we have a touchscreen that can accept 40 points of contact. Do you think that the ability to recognize the signature of a person's swiping style would ever get sophisticated enough that you can tell which user is doing which, swipes and interactions just based on their, on their individual signature and finger shapes and all that kind of good stuff?
I think so, actually. I think I've read work where they do use the style of interaction with the phone to identify people. It's one of the ways they have the personal protection. Instead of having a passcode, it looks at the way that you type or write. So I think I have seen papers on that, so I do believe it should be possible.
Okay. And then the second thing is, based on the accelerometer,
Yes, sir?
do you think it would be possible to get, a pattern for how the person holds the phone, the angle that they hold the phone, and, basically the telemetry of the accelerometer, so you would know who's holding the phone if you're just using the phone?
Based on the accelerometer, I think probably you'd rather use the gyroscope because then that's really showing how you're orienting the phone rather than how you're moving the phone.
Moving it, right, okay, I was thinking of moving it here. Okay, very good. So, yeah, tell me about that for a second. Do you think that's possible?
I think it's something interesting to look at. I mean, although people probably hold phones differently depending on what situation they're in. If they're looking at something more sensitive, they probably hold it closer to themselves than if they're just texting somebody normally. So there might be something there. It's something to look at.
Okay, yeah, and I know it's a little unfair because it's, you know, a little outside of your thesis question, but I thought, you know, like,
Okay, it's fine.
you certainly would have enough grounding to answer right now.
Thank you for the questions.
Okay, thank you.
Yes? Oh, can we use that if somebody has a question? I know I said it in here somewhere. Okay, so they sample every 5 microseconds.
Oh,
Yeah.
God,
So
very different.
much different from what I thought.
Yes, yes.
So you're getting like around 20 samples per second, something like that. Or no, much less, much more, sorry.
So if it is 5 microseconds, it's, you know, 5 to the minus 6.
So
Yep,
maybe I was looking at an
Much,
older
much
photo
better.
and it was,
yeah, much,
Yes,
much better.
yeah.
I was thinking that you could really maybe detect tremors in there, you know, low frequency, but good.
yeah, every 5 microseconds. Yes. Any questions?
Yeah. Can you try to left-handed person and see if it works?
Pardon me?
Try that with left-handed person and see what you get. See what the outcome is going to
I'm
be.
sure it would work.
This is the regular for the work, right?
That's true, yeah.
Thank you, Trey.
Thank you.